Okay, let's see. So iron rusts as follows. Iron rusts as follows. The reaction is 4 molecules of iron solid metal. You know what? Let me write this a little more clearly here. These straight lines again. So 4 iron solid plus 3 molecules of oxygen gas form 2 molecules of Fe2O3. Well, Fe2O3 is not really a molecule per se. It's an ionic compound, so it's sort of an extended crystal, if you will, to Fe2O3. Now, find, well, I'll say, ooh, oh, these lines, I don't know what it is about these things. They're just all over the place. Okay. Using a thermotable, in other words, the table of thermodynamics data, using a thermotable, find the K. Find the equilibrium constant for this reaction. Find the K at 25 degrees Celsius. Oh, okay, well, we know how to do that. They want us to find K. Well, we know the reaction. We know the relationship is delta G equals minus RT ln K, right? We're at equilibrium. We just solved that reaction, the equation by setting the delta G reaction equal to 0. So let's go ahead and use this version of it. K is equal to E minus delta G over RT. Okay, so let's find our delta G. Well, our standard free energy change, well, it equals products minus reactants. So you're going to end up with 2 times negative 740 minus 4 times 0 plus 3 times 0. Oxygen gas is an element. The free energy is 0. Iron metal, anything that's elemental, anything in its element form, free energy is 0. So that doesn't count. So the delta G ends up being a minus 1480 kilojoules, right? 2 moles times negative 740 kilojoules per mole. That's minus 1480 kilojoules. So now we write K is equal to E to the minus 1480000. We have to work in joules because R is in joules per Kelvin. R is 8.3145 and temperature is 298. I'm sorry, this is minus, so minus. That minus sign is not part of the delta G. So minus delta G is negative, so it's minus minus. There we go. So we end up with, when we do the math, E to the 597. Now, what can you tell me about E to the 597? Is that a big number? Yes, that's a massive number. It's absolutely massive. That means that when you see an equilibrium constant that's this big, that means that once this thing reaches equilibrium, this reaction reaches equilibrium, it is so far to the right that literally there is absolutely no reactant left. There is no iron and there is no oxygen gas left. It is so far to the right. So it basically, this is what we would call completion. Now, this is still equilibrium. The fact of the matter is there's always going to be a few, atoms of iron left, and certainly oxygen you're never going to run out of because oxygen is in the atmosphere. So the limiting reactant in this particular reaction is going to be the amount of metal that you have rusting. Well, it's true. It's going to reach equilibrium, but see how high the equilibrium constant is. That means that the products are so much and the reactants are absolutely 0. This is virtually infinite. In fact, this is infinite. So it is equilibrium, but a high equilibrium constant pretty much tells you you're talking about something that is completion. There is no reactant left. It's all product. Okay. We would call this thermodynamically favorable. So you'll often hear this term. Is this reaction thermodynamically favorable or unfavorable? Yes. As written, this is thermodynamically favorable at 25 degrees Celsius. The equilibrium constant is very, very high. And clearly the delta G is very, very, very negative. Minus 1,480,000 joules. That's extraordinary. Thermodynamically favorable. So in some sense, as you see, the free energy and the equilibrium constant are sort of almost the same thing. They tell you what's going on, but there is a relationship between them, and that's it. They're not the same thing. I'm sorry.